Well, I hope everybody can hear me and see me, and I never lost it like this before, so I apologize. So, all right, I am going to begin. Good evening. Welcome to tonight's STEM Cafe, Earthquakes and Fracking. Thank you for joining us for an earth-shaking discussion of seismic activity in the northern Illinois and the central United States. Our STEM Cafes are brought to you by NIU STEAM and the Center for P20 Engagement at Northern Illinois University. I'm Dr. Judy Diamond, organizer of the STEM Cafes for the past 8 years and your host for this evening. I was just checking to see if everybody could hear me and see me. NIU STEAM refers to science, technology, engineering, art, and math. STEM Cafes are designed to be fun, casual gatherings where adults can eat, drink, and chat with STEM professionals about the hot topics and the latest research. We usually hold our STEM Cafes in restaurants and look forward to getting back to the restaurants. Tonight you will have to provide your own favorite snacks or favorite carryouts and drinks. But in the meantime, a couple of our partner restaurants are offering specials for virtual STEM Cafe participants. Fatty's Pub and Grill in DeKalb is offering a 10% discount to anyone who mentions that they attended one of our virtual STEM Cafes. The Open Range Southwest Grill in Sugar Grove, our partner for both teen STEM Cafes and adult STEM Cafes, and will be our partner for our next STEM Cafe, is offering $5 off to anybody until July 31st if they mention they have attended a virtual STEM Cafe. For those of you that have not attended our STEM Cafes, our format for this evening is as follows. Our speakers, we have 2 speakers, will talk for approximately an hour. During the talks and following the presentations, feel free to write in your questions and comments. We know there are many experts in the audience as well, so often our attendees add to the discussion with their comments and insight. I see that some people already have put in some questions. We will end by 8 p.m. If you experience difficulty hearing at all tonight during the presentation, you can find a volume control in the top left corner of your screen for you to adjust that to your particular liking. This cafe will be recorded. It will be posted on our website in about a week, as we need to make sure that we have closed captions so that it is acceptable to all. Tonight, our topic is earthquakes and fracking, and we will feature 2 speakers, NIU geology professors Dr. Brown and Dr. Carpenter. They will engage us in an earth-shaking discussion of seismic activity. Tonight, I have the pleasure to introduce Dr. Phil Carpenter, professor, and Dr. Megan Brown. Dr. Phil Carpenter will speak first. And a little bit about Phil. He has his PhD in geosciences, specializing in geophysics, and is a registered professional geologist in Illinois. He has been interested in the earthquake history of northern Illinois since starting at NIU. Prior to NIU, he worked as a seismologist at Los Alamos National Laboratory in New Mexico, where he studied earthquakes in the southwestern United States, as well as working on seismic verification of underground nuclear tests. NIU operates a seismograph station on its NIU campus, and Dr. Carpenter periodically provides information to the media when a newsworthy earthquake occurs. In recent years, Oklahoma has experienced more felt earthquakes, which means a magnitude 3 or higher, than California. 26 minor earthquakes have rattled northern Illinois in the past 100 years. Tonight, Dr. Carpenter will discuss where faults are located in the northern Illinois region, and what unmapped faults might be active here. Our second speaker, Dr. Brown, assistant professor, is a hydrogeologist that uses computer modeling and geophysical techniques to study injection-induced earthquakes. She joined the Department of Geology and Environmental Geosciences in August of 2019 after earning her PhD in geological sciences from the University of Colorado Boulder. She received her master's degree from the University of Missouri Columbia. Prior to graduate school, she worked as a geologist in a small environmental consulting firm in the Mid-Atlantic, where she worked on the remediation of hydrocarbons. Tonight, Dr. Brown will be talking about induced earthquakes. She will discuss several of the known and potential ways of triggering induced seismicity, as well as mitigation plans and procedures, and how it is being addressed in the central and eastern United States. Thank you for being with us tonight. I'm going to ask Dr. Carpenter to go ahead and begin.
Hello, everyone. Can everybody hear me okay? We're going to launch right into the presentation here. So I've been at NIU for about 32, 33 years. And one of the first things I started to look at when I came here was earthquake history of northern Illinois. And there are a lot of interesting quakes that we've had somewhat recently. Many of you will remember this one, which probably woke some of you up early in the morning of February 10th, about 4 o'clock in the morning. This was a magnitude 3.8 earthquake that basically shook the whole Chicagoland area. We'll talk a little bit more about it. One of the interesting things was it was a real surprise to have an earthquake in Lily Lake because we have no mapped faults in that area. So that's one of the things we'll talk about in the last part of my talk. Here's just some, some of you might remember these, some of the publicity that earthquake got. We had camera crews on campus for about a week and a half afterwards, plus numerous write-ups and articles and things. There's another picture of it, a little bit more enlarged. One thing we'll also discuss are these different types of waves that you see on a seismogram, obtained through a seismograph. So kind of breaking the talk down, we'll go over some of the basics on earthquakes, like what are faults, how do we record earthquakes, and analyzing seismograms. Then discuss some of the earthquake history in northern Illinois, some of the faulting that we have here. And then we'll very briefly talk about some of the earthquake hazards in southern Illinois and in what's known as the New Madrid area, which many of you, I think, are familiar with, 1811 and 12 earthquakes. So earthquakes occur when you have a broken zone along a rock called a fault. And this, I think, has gotten cut off here a little bit, but you strain the rocks to a certain degree, and then they snap, basically. And that's when you get an earthquake. So the earthquake is along the zone that breaks here in response to stresses in the earth. So here's another picture. Stress builds up. You distort the rocks, and then they break suddenly. And here's a classic picture from the 1906 San Francisco earthquake. It shows an offset fence above a fault, above the San Andreas Fault. So just some terminology that is commonly used. Usually when you read media accounts of an earthquake, they'll mention where the epicenter is. The epicenter is actually the point at the Earth's surface directly above where the fault breaks. So the focus is where the actual earthquake occurs, and that's usually about 10 kilometers to 15 kilometers, or about 6 to 10 miles below the Earth's surface. So you generally can't see these directly. What you can do is you can locate the earthquake, determine estimate its depth, and then get some idea where the fault actually is. So there's three basic types of faults. The kind that we looked at in the previous picture where the fence was offset, that's a strike slip fault, where you have horizontal motion. You can also have a vertical motion where one rock mass is pushed up over another. That's called a thrust fault. And then another very common type of fault is a normal fault, where one piece slides down next to the other crustal area here. So these are the three basic types of faults, but you can also get combinations of all three of these. So here's the classic strike slip fault, the San Andreas fault. You can see this stream here has been pushed over. This is going north, and this is going either stationary or going south, so you can see the diverted stream right here. Another type of fault is a normal fault, and you can see here, this unit right here, this black unit is offset. And this piece has gone down relative to the section on the right. The third type of fault is the reverse fault. This might be a little bit harder to see, but you'll notice this kind of light gray brown unit has gone up relative to this side over here. So those are the three basic types of faults. And we already got a question about this earlier. This is the Sandwich Fault in northern Illinois. It looks like a pretty grungy, crumply area, so it's hard to see any offset here, but it is actually a normal fault. So far, it looks like it's inactive. We don't have any evidence of recent displacement on this fault, but it's one of the few faults in northern Illinois that we can actually see. This picture was taken at the railroad cut in Oregon, Illinois, where it's one of the very few exposures of this particular fault. So how do we record earthquakes? This is a conceptual picture of a seismograph. So you have a frame that's anchored to the earth, hopefully in a quiet location like a basement or in a separate vault. And then you have a weight suspended here. And as the earth moves up and down or back and forth, this weight will inscribe a squiggly line here called the seismogram on what used to be a piece of paper, which would be rotating. You can see as this moves up and down, then this stays relatively stationary. The earth is moving relative to this weight, so you get this squiggly line. And there are different types of waves that you'll see here. Usually the first wave is called the pressure wave or the P wave. That's the primary wave. That's a sound wave. So it's the same kind of wave you get from air molecules that are moving. So particles in the earth are being squeezed or stretched in a three-dimensional manner. The second type of wave you typically see is the S wave, known as the shear wave. That travels slower than the P wave, and it's kind of an up and down shaking or back and forth shaking. Then on larger earthquakes, you also get surface waves, which tend to be the strongest waves. You generally need a magnitude 4 earthquake or larger to see these. And they also have back and forth twisting type motions that cause a lot of damage to structures. So again, this is just another picture of the P wave, the S wave, and surface waves. And this is kind of a cross-sectional, two-dimensional image of it. P moves out first, then you have the S wave behind the P wave, and then the surface waves follow. So in the Lily Lake earthquake seismogram, here's the P wave right here. Then there's the S wave right here. There might be surface waves back here, maybe probably around here, if there are any from this earthquake. It's a pretty small earthquake to generate surface waves. You also see a lot of other arrivals in here, and these are some of the things we like to study. These are little reverberations in the earth between different layers, reflections off deeper layers. So there's actually a lot of information contained in these seismograms. Here's another seismogram. Some of you might remember this earthquake occurred on April 18, 2008. And again, this was recorded at our seismic station here at NIU. It was a magnitude 5.2 earthquake occurred in West Salem, Illinois, down in the Wabash Valley. But it was felt actually this far north. And here you can see other multiple arrivals. Here's the main P arrival. Here's the S arrival. And there appear to be some surface waves out here later on. So larger earthquake, a little bit more complex seismogram. And we'll see if this works or not. This is supposed to be an animation showing you the waves. That's going to work. But you can, oh, there we go. See a little bit of it. Let's go back. Here's the P wave. You see it's compressions and dilatations of these different elements. There's the S wave. It's an up and down motion. It can also be a back and forth motion. And what this is actually supposed to do is crumple up this house here as it goes by. Does not seem to be playing. And then the surface waves are kind of like S waves, but then they mostly travel along the Earth's surface, and they die out with depth. That's why we call them surface waves. And this shows all three of them. So you get the P wave, then the S wave, and then the surface wave behind that. So when people want to come and see the seismograph, this is what they expect to look at. The recording drum here is what we call this, which has basically one line going all the way around for 24 hours. You have a clock, you have a pen here. And these little things we see here, these are trains going through DeKalb. We have about 55 trains a day go through DeKalb, so we pick up a lot of train signals. Well, the problem with this type of system is people forget to change the paper, and then invariably an earthquake will occur. The pen clogs, and so you miss the earthquake then, or your clock might go out. So we have moved on to a digital system. So we have the seismograph in the basement of Davis Hall, and there's a cable that goes to a digitizer, which then goes to a computer, which you can actually see. It's on display in the lobby of Davis Hall, kind of on the east side of the building, foyer. So that's on display, so you can watch what's happening when they open campus back up again. We can also hook that up to go up on the internet, and then to an external connection as well. So that way we're not going to miss something unless the power goes off. Even then we have a battery backup. So it's a much more flexible system. Here's a comparison of the old-fashioned paper record. This is the Sumatra earthquake, one of the earthquakes that caused that huge tsunami, 2005 to 2004. It's 2005, actually. And then the Chile earthquake in 2010, one of the biggest ever recorded. You can see the P wave here and then the S wave. And the nice thing about the digital system is you can replay this as many times as you want. You can change the magnification on it, squeeze it, spread it out. You can do all sorts of things which you can't do with the paper record. So that's why you won't see the recording drum anymore. You'll see a digital computer output. So how do we locate earthquakes? There's a number of ways of doing this. The simplest way is through triangulation. So P and the S waves leave the focus at the same time, and then as they pass through the Earth, the P wave starts outrunning the S wave. And the amount of time between the two will tell you how far away the earthquake is. So the bigger the S minus P interval, the further the earthquake is from the station. So if you have 3 or more stations, you can do this. You can draw circles around the station, and they'll hopefully intersect at the epicenter. If you have more than this, you can actually make a rough estimate of the depth of the earthquake as well. So if you plot out epicenters for, say, North and South America, this is the pattern that you'll see. Most of these occur along what we call plate boundaries. A plate consists of the crust in the upper part of the mantle that's rigid. These plates are moving around on the Earth. Some of them are spreading apart, some are colliding, and that's where you have most of the earthquakes. You'll notice the west coast of South America, all through Central America, the San Andreas Fault Zone through California, where we have 2 plates sliding past one another, and then the Aleutians, of course, up here. You have a plate being pushed under another plate. We're not going to really focus on that tonight. We're more interested in these earthquakes that occur in the continent away from plate boundaries. So most earthquakes occur on plate boundaries, but not all of them. And these ones that occur in the central part of the U.S., the western U.S., up along the eastern U.S. are pretty interesting, pretty mysterious types of earthquakes to look at. because you can't just simply explain them through these plate boundary interactions. So if we zoom in on the United States, the continental U.S., this is a pattern we have right now. And you can see, again, most of the earthquakes are occurring out in California related to the San Andreas fault system. But there are a lot of earthquakes in the mountain areas, like around Salt Lake City, Idaho, Wyoming. Central U.S., right? We'll talk a little bit about this at the end of my talk. And then Megan is going to talk about Oklahoma and some areas out in Colorado. So it's kind of surprising, some of you may not realize it, like Charleston, South Carolina had a big earthquake in the 1880s. A number of earthquakes in New England. Well, okay, so the other thing I wanted to mention was magnitude scales. There's a lot of confusion about magnitudes. That they used to use the term Richter magnitude, Mr. Charles F. Richter. That's pretty much not used anymore. There's other magnitude scales that have been used, particularly this MW, which stands for moment magnitude. So one of the confusing things, I think, sometimes can be that an earthquake that was had, I think, a magnitude 8.3 now has been reclassified as a magnitude 9.5 with a different scale. Each point in magnitude corresponds to approximately 10-fold increase in shaking and a 30-fold increase in energy release. If you look at a, say, magnitude 3 earthquake versus a magnitude 6 earthquake, you get about 27,000 times energy released. The magnitude 6 quake, which is why you get all the damage at the higher magnitudes, very little damage at the lower magnitudes. I think this next slide kind of illustrates that graphically. So magnitude 6 to magnitude 8, there's going to be a 300-fold increase in energy release and a 100-fold increase in amplitude. So it's a logarithmic exponential type of scale. So it goes up to about 10. And of course, very, very strong earthquakes are up in the 9s here. When you get down around 2, below 2, we call these micro earthquakes. They're generally not felt. Or minor quakes like the Lily Lake 3.8, magnitude 3.8 earthquake. I have talked to people that have felt quakes as small as about 2.5, 2. If you're sitting right over the focus, you can feel those quakes. We had one in Lake in the Hills, I believe, a few years ago, and that was like a 2.1. Some people still felt it. A few hundred people felt it. That's kind of interesting. But generally below 3, it's hard to feel them. Smaller earthquakes are much more abundant than the very large earthquakes. This is kind of a equivalent energy release. Here's the magnitude over here, and kind of equivalent other events. So an average tornado, say, corresponds to about a magnitude 4 to 5 earthquake energy release. And when you get down to the lower part of the scale here, you can't actually record all the earthquakes that are occurring, say, at the magnitude 2 level or below. There's lots and lots of really small earthquakes that probably do not get recorded or noticed. Okay, so that's magnitude. There's another scale called the intensity scale. This is referred to as the modified Mercalli intensity scale, and it's based on what you feel and what you observe and types of damage that you can see. To avoid confusion with the Richter or the magnitude scale, they use Roman numerals for the intensity scale. So here's the intensity scale. Number 1, it's only detected by instruments. Number 2, very feeble. Number 3, slight. And it goes all the way up to damage to structures. For instance, a very typical type of damage is chimneys fall. You usually get that around intensity 8. These roughly can correlate with magnitude, but magnitude is more of a numerical instrumental scale. This is more based on your own observations. For instance, this is the intensity map for the 3.8 earthquake, the Lily Lake earthquake. If you go to the U.S. Geological Survey earthquake hazards website, they will have, I don't know if you can see it over here. Did you feel it up here right at the top? you can type in what you felt, and they'll generate a map like this for intensities. I know with the Lily Lake earthquake, the earthquake occurred at 3:59. By about 4:05, they already had a preliminary location, and they already had a map like this generated by people that were typing in what they felt. So, pretty efficient way of collecting that information. Okay, so let's move on then and talk about some of the earthquake history of northern Illinois. And more on the February 10th earthquake. So this is where it actually occurred. This is where the epicenter is. Here's Lily Lake. This is Highway 47, and then this is Highway 64. If you actually look at the site, there's not much to see. It's a farm field that was right around this area here. So there's no evidence whatsoever at the surface of any faulting, or you can't even see any rocks, because this is all covered by glacial deposits. So because there's an earthquake, you know there's a fault there. Consider that a previously hidden fault. So if we look at the earthquake map, let's go back here a minute, of northern Illinois, the little red dots are earthquakes that have occurred over about the last 200 years. And of course, our record's not complete for the earlier earthquakes. One thing that really stands out, though, is these dots are not aligned with the two major fault systems in the state. Here's the Sandwich Fault, which is the major, probably the longest fault in northern Illinois. It's only exposed at the Sandwich Quarry, and then up, as I showed you earlier, the railroad cut in Oregon, Illinois. And the rest of the length of this fault is defined from water wells. You're noticing strata that's been moved, displaced. So it's a normal fault with the south side up, the north side down. There are some clusters of earthquakes. There's been a number of earthquakes in the Fox River Valley. There's a cluster over here around the McCook Quarry. Some of these may be quarry-induced earthquakes. There's been a cluster out in the Quad City area, and then some other areas. This area around Dixon is kind of interesting. Earthquakes in this area. But again, what's striking is none of these red dots lie on top of the faults. So I'm going to talk about a few of these earthquakes. The biggest one in northern Illinois was the 1909 September 26th earthquake. And we don't really know where that epicenter is. I'm putting it up here on the state line because the greatest intensities were noted in newspapers from around Beloit, that area. More recent work has actually placed that, well, there's been about 5 different locations based on the newspaper accounts. For a while it moved over to Aurora, then another researcher put it in southern DeKalb County. Somebody else put it over here more toward Oregon. So we really don't know where the epicenter for that magnitude 5, estimated magnitude 5.1 quake is. And here's a couple of newspaper articles. This is the Rockford Register Gazette. And this was kind of an amusing picture. It was felt in downtown Chicago, especially in the skyscrapers. So it gained a lot of attention. Again, there were no instruments in the area at the time, so it was not recorded instrumentally. A couple other areas that are interesting. We mentioned the Quad Cities over here in the 1930s. There was a swarm or cluster of earthquakes there, and then look at this area around Dixon, Amboy. That's had a couple of earthquakes. There's another one near Ottawa. Some of you might remember that one in 2004. If you look at the distribution over time, these are not randomly distributed. There are periods where we have more activity and periods where we have less activity. So between 1972 and 1999, that's quite a long span of time. There were no earthquakes that we reported or were recorded between that time. Since 1999, there have been several. So we seem to be in a more active period right now. So here's these are like intensity contours for one of the Rock Island earthquakes back in the 1930s. They got up to intensity 6 here. Minor damage associated with these earthquakes. Here's these 3 quakes that occurred between 1972 and 2004, kind of in the same general area. 72 quake was the first quake instrumentally recorded from northern Illinois. There was a station at Loyola University that recorded that earthquake. and then the 99 and the 2004 both had pretty extensive recordings, so that they could be located with precision and we could study the waveforms fairly well. But notice they lie along a structure called the Peru monocline. This is a warp in the rocks that are, again, none of this is visible. It's all buried by glacial deposits. But from water wells and other types of drilling and exploration, we know it's there. What might be happening is that we have, here's a 2004 earthquake near Ottawa. Some of you probably felt that. There's the intensity map for that. It was felt all the way up into Wisconsin. So that area, this is what might be happening in that area. You've got a warp, so this would be like the Peru monocline. Geologists call this a fold. And then below that, we believe there's a fault. The fault has propagated upwards as a fold, so it kind of stops right about here. And we really don't know much about the deep bedrock in this area. It's probably granite, but some kind of igneous rock underneath all the sedimentary rocks underneath the glacial cover. So we really don't know what's going on down here. Some possible causes for seismicity have been suggested. If you look at the stresses, you can do that by looking at different see, I guess we're not seeing the pointer here. Okay. 0. There we go. Okay. There we go. Horizontal stresses could be causing these, reactivating older structures. Glacial rebound. There's a possibility the glaciers covered this area up to about 13,000 years ago. And then it's been suggested that seismicity might be related to climate. We get more seismicity after a wet summer. Seem to see some indication of this. So that's kind of an interesting idea. Again, going back and looking at earthquake epicenters, hopefully everybody can see the arrow now. We have this zone, kind of diffuse seismicity in northern Illinois, then pretty much a dead zone in the central part of the state. And you'll notice in southern Illinois, we have lots and lots of earthquake activity. Pretty much have a felt earthquake every few months down there. And this kind of aligns along certain zones here. This is the New Madrid seismic zone here. And up further here, this is the Wabash Valley. So just want to talk very briefly about these areas. These are the main seismic hazards in the central U.S. And New Madrid is down here in the boot hill of Missouri. And then the Wabash Valley is up here. This is where that West Salem earthquake occurred that I showed you earlier in 2008. So this New Madrid area is notorious for 3 earthquakes that occurred in 1811 and 12 that were in probably the magnitudes upper 7s, low 8 range. That's further from Chicago than in the West Salem area, and there's been evidence that there have been prehistoric earthquakes that are quite large up in this area, somewhere in the 7, which could pose a threat. Our area were large enough. So what's believed to again happen here is we have old faults. You can't see any of this stuff at the surface. So you've got in the Wabash Valley and New Madrid, especially New Madrid, you've got all the sedimentary cover along the Mississippi River as well as other sediments. But deep, deep down is believed to be an old rift zone with igneous rock bodies that are very dense. And for some reason, it's called the Reelfoot Rift based on Reelfoot Lake, which is in Tennessee. That lake was formed by the 1811 and 12 earthquakes. It's believed to be down here some kind of faulting that's being reactivated, some process. So the U.S. Geological Survey and other organizations are very concerned about this area for a repeat of the 1811 and 12 earthquakes. One of the other things is, we talked about intensities earlier, those earthquakes were felt as far north as Boston. That's the 3 up here. We don't have any data really from how far west it was felt. So one of the things about the eastern and central U.S., if you have a major earthquake, it'll be felt over enormous distances. It probably will cause a lot of damage over a large distance as well. So if we compare those two earthquakes, those 3 earthquakes in central U.S. to similar sized earthquake, the San Francisco 1906 earthquake, to see how much smaller the intensity, area of high intensities is in the west versus the east, probably kind of the type of rocks that we have in California versus the type of rocks that we have in eastern and central U.S. The rocks here are older, they're more consolidated, denser, more rigid. So earthquake waves can propagate over enormous distances in the eastern and western U.S. In fact, recently, I think a couple of years ago, we had reports from people in Rockford and Beloit feeling an earthquake that occurred in Ontario. So earthquake waves propagate very efficiently through the eastern and central U.S. So what people do, like from the U.S. Geological Survey Earthquake Hazards Division and other groups, is they construct these hazard maps, look at the probable acceleration, typically over a 50-year period, called probabilistic hazard maps. I know you can't read the numbers on here, but the colors show you areas that are more likely to have damage. We are not really in one of those areas. We're in kind of this grayish color. And you can see again, New Madrid area, areas in Tennessee, and then Charleston, Carolina is also a hazard area due to that 1806 earthquake. The Iron Mountain seismic belt here, and then of course pretty much all of California and most of Nevada rated as highly kind of a risky area for earthquakes. This map was generated earlier. You'll notice there's a little bubble here near Oklahoma, but that's being revised continually, so the hazard there is probably increasing as well. Okay, I think that's about it here. End of my session. I think we'll turn it over to Megan and turn my camera off.
I can just take it away if you're done, Judy. Okay. So, like Judy said, this is my first year here at NIU. I just finished it, which is a pretty interesting way to start my faculty career. But my research area really has focused on induced earthquakes, and in particular, injection-induced earthquakes. And so tonight I'm going to talk about induced earthquakes, but then also kind of step back and talk about oil and gas in general, and also fracking in a little more detail. Turn on my pointer. So injection-induced earthquakes induced earthquakes in general occur all across the world. And there's a variety of different types of things that can induce earthquakes. Induced earthquakes are really just earthquakes that have been triggered or caused by human activities. And that could be things like quarries and mining, extraction, which would be oil and gas extraction, where they're actually producing the oil and gas. Reservoir induced, this is where a reservoir is being filled, like a drinking water or recreational reservoir. My PowerPoint went away. Okay. It's coming back. Hopefully everyone can see that. And then there's also fluid injection induced, and that's the one that I'm really going to focus on tonight. This includes things like fracking, also geothermal systems, geothermal energy systems, and then also wastewater disposal. During the oil and gas production, there's a lot of water that's also produced, and I'll talk about that in a little more depth. Okay, so some of the injection-induced earthquakes can occur during enhanced oil recovery, and this is when you have an oil and gas well, usually a well that's been fracked, that's being produced. And to help increase production, they'll inject fluids into the production formation that literally push the oil and gas towards the production well. And so you end up having this system where you have fluids going in, oil and gas coming out. And during this, the companies like to keep the pressure of this formation consistent. So, sorry, it keeps changing on me. And so, where did my pointer go? Okay. Sorry, I'm trying to get my pointer back. It's not coming, so we'll just describe it in words. So the oil and gas is being pushed by that injection and then produced. It's staying a consistent pressure. So then there's some induced earthquakes that occur with this, but a lot less than some of the other types of injection-induced earthquakes. So one of the main ones I'll talk about tonight is hydraulic fracturing. Hydraulic fracturing is really just when you are injecting at very high pressures for the purpose of breaking the rock. And this is because the formations that are being produced out of the oil and gas is coming out of is very low permeability. And that just means that fluids don't flow through the rock very well. So to help increase that permeability and be able to get more oil and gas out of the formation, they inject at really high pressures to literally break the rock, which causes microseismicity. Most of it is microseismicity, so that's the lower than magnitude 2. It can even get down towards negative magnitudes of earthquakes. There are some larger earthquakes that occur right with hydraulic fracturing. This tends to happen more in Canada. And then also there has been some studies in the US and Oklahoma and Texas that have looked at this, but they tend to be more solitary, like just one larger earthquake and confined to a smaller area. When you start getting the larger earthquakes, we're really looking in the crystalline basement, which is down at the bottom of these graphics. And these are where the larger faults are, and fault size is directly correlated with earthquake size. You have to have a larger fault to have a larger earthquake. And so these crystalline basement rocks, those are your hard, metamorphic, igneous rocks, things like granite, gneiss, everything you want to make countertops out of. This is where those larger earthquakes occur. And because the production zones are much higher than the basement usually, and because they're sealed, because you have to keep the oil and gas in those production formations, so there's typically low permeability rocks around it, the injected fluids don't travel down towards the crystalline basement, and the pressure doesn't propagate down towards the basement. So these tend to be smaller earthquakes. You can also have earthquakes from the extraction process. I'm not going to talk about that today. And then the main area that I've researched and that causes a lot of the injection-induced earthquakes is wastewater disposal. So this is where you have water coming up with your oil and gas. When you're producing a well, you have just water that was already in the production formation in the rocks coming up to the surface as you pump out the oil and gas. It tends to be very salty. and in large volumes. And so it's not cost effective to clean it at the surface. Some of it will be reused and recycled, but most of it has to be disposed of. And so how they dispose of that is by injecting it in deeper wells, like the well on the right of this image. And they're going to inject it into formations that are more permeable. Fluid more easily goes through the rocks. These formations tend to be much deeper than the production formation and a lot closer to the crystalline basement. So these wells are able to have pore pressure diffuse or propagate down into the basement, which is what the main triggering mechanism for induced earthquakes is. So I'm going to step back, talk a little bit about oil and gas and then fracking. These are probably some images you might be familiar with from media. On the left, there's a picture of a drilling rig that can drill oil and gas wells. On the right, there's an image showing a frac stack while they're actually hydraulic fracturing the oil and gas well. Behind it, which might be a little hard to see, there's containers that hold the fracking fluid and also pumps that are used to inject into the well. And you might have seen these, as you're driving around different parts of the country. On the left is a pump jack, also sometimes called an oil horse. And this is just a pump that pumps out oil and gas. And then on the right is the top, right at the surface, there's a wellhead, and on top of it, this isn't a very good one, but a lot of times they'll have what they call a Christmas tree, and shows different, it's kind of shaped like a Christmas tree. And this is the valves that allow the oil and gas to come up. So this is when the oil and gas wells have been finished and are actually producing oil and gas. I feel like I can't really ever talk about oil and gas production or induced earthquakes without talking about economics and kind of some geopolitical things. So this is just a graph that shows on the y-axis energy consumption and on the x-axis GDP, so gross domestic product, which is just a measure of the wealth of a country. And you can see it's pretty well correlated between how much energy is being used and how wealthy the country is. And we still can't get a pointer, so sorry guys. Oh, there it is. We're right here. Here's the US. So most of the oil and gas that's produced and used in the US is used for transportation, but we also use it for electricity. This is just a graph showing the amount of electricity generated versus the time from 1950 through 2019. You can see from 1950 through 2007 maybe, there was a pretty steady increase in consumption, and then it kind of leveled off. Most of our energy production has come from coal, but as coal decreased in recent years, natural gas has really taken up that space, and a little bit with renewables, which is in the green. And there's a lot of controversy in terms of whether natural gas is a transition fuel, because it's able to turn on turbines really quickly so that it could kind of take the place when you have solar energy when the sun goes down, or wind energy when the wind stops blowing. Some people don't like that term, but that has been something in the media. And in recent years, we've had a lot of oil and gas production, and a lot of that started in 2008, 2009, when the price of oil was very high. It got over $100 a barrel. Right now, it's about $40 a barrel for comparison. And this graph is just showing how much we have imported LNG, which is liquefied natural gas. You can cool natural gas a lot, and it liquefies. It makes it a lot safer to transport because it's not at high pressure. And so you can see on the blue line, we've done a lot of importing of LNG, but now, in recent years, we've exported more. So we're a net exporter now. So oil and gas forms pretty basic process, or I'm going to explain it in a really basic way. This is where you have plankton or dead marine animals. They settle to the seafloor. They're going to be covered by sediment that restricts oxygen. As they're buried by more and more sediment, the heat and pressure increases, and you have chemical reactions that produce the oil and gas. And then you have, geology happen where you might end up with a fold or some other type of trap that, as the oil and gas moves towards the surface, it traps, usually with some kind of cap rock, a low permeable, hard to flow through rock, and it captures that oil and gas. And so the oil sits on top of the groundwater and the natural gas on top of the oil. So no matter what you've been told, or what a really interesting logo has given you an idea of, oil and gas does not come from dinosaurs. It comes from plankton. I know it's not as fun. But so there's a couple different types of oil and gas traps. And one of them is just like I showed in the previous slide, a fold that has an impermeable or low permeability, something like a shale where fluids don't flow through very easily. And so that fold traps the oil and gas. You might have a void space in something like a limestone with shales on top, so it's trapping again. You might have a fault. These are all cross sections, so if you cut into the ground and look at it from the side. So this is a fault, and maybe an offset takes that permeable rock where the oil and gas is being trapped next to an impermeable rock that actually traps it, or you could have something like salt also create a trap. So there's two main types of drilling and oil and gas production that we talk about. One is conventional and one is unconventional. Unconventional is kind of a misnomer now because it's pretty conventional, but we still use these terms. So conventional drilling is the old way of drilling, and you can think of it as a jelly donut. So you're going to drill a well straight down into the center as if the jelly is your oil and gas. And then you're able to pump it up pretty easily. The unconventional or new way of drilling, this is where you have hydraulic fracturing. This is where it's a little more like tiramisu. So one of these chocolate layers is your area that has oil and gas is able to be produced. And now that we have the technology to do really successful horizontal drilling, sometimes 2 miles out from the actual turn from the vertical part of the well, you can have contact all the way through that layer. And then when you are able to hydraulically fracture it, because this is usually a low permeable layer, not easy to flow, by making those cracks in the rock, you're allowing more oil and gas to come through because you're increasing the permeability. So this is an example of one of those horizontal wells. When these wells are drilled, they have multiple layers of steel casing in them. Once they're finished drilling, they go through a completion stage, and that's when the hydraulic fracturing occurs. So this well will have, like I said, steel in it. You'll take water and sand. That's the vast majority of the fracking fluid. There is some chemicals in it because to stop like liming and different things in the well. So how this works is they block off the first section of the well called the toe, and they'll do it in small stages. So it'll be a small section at the front of this, at the end of this well, and first they'll put a perforation gun down and blow holes in the steel, and then they'll inject that frac fluid. It's made mostly of water and sand at really high pressures to break the rock. And as they break the rock, the sand moves into the cracks and is able to keep those fractures open so that you increase the permeability. Then they'll block off the next section of the well and do that again and again all the way to the heel of the well, which is that turn. This is done usually over several days. And after this is done, you're able to start producing the well. The initial part of production, you do have some flowback of some of that fluids that were used in the fracking. And then after that, you end up with those produced waters, that salty water that was already in the formation and that needs to be disposed of because there's just too much of it and it's too hard to clean at the surface. There's definitely active research going on how we could clean it on the surface, but right now it's still being trucked mostly to wastewater disposal wells. And a lot of time those wells are commercial, so oil and gas companies pay for the water to be disposed in these deep injection wells. So I want to just kind of show you a basic map of some of the basins. I'm not sure how large this will be on your screen and if you can read it, but these are different basins across the country. The darker orange shows shale plays. These are often or almost always going to be hydraulically fractured. These are not the only types of plays. Plays is just an accumulation of oil and gas that can be produced. So these are not the only type of rocks that oil and gas accumulates in or is fracked. In the Denver Basin, which I'm much more familiar with, there's sandstones and also different limestones that are produced out of. We do have some oil and gas in Illinois. It's mostly in the southern part of Illinois here. It's mostly vertical conventional wells. The oil and gas production started in the mid-1800s, and they started fracking those vertical conventional wells in the 1950s. Hydraulic fracturing is not new. It's been used really throughout the 1900s for over 50 years. And it's just really picked up pace because of the horizontal wells now. But in Illinois, there's been tens of thousands of wells over the little less than 200 years of oil and gas production. But now the wells are mostly producing at a low to moderate rate. It's not the largest producer in the country. So now I'm going to jump back to induced earthquakes. This is a map of the central and eastern United States. All those blue dots are all the earthquakes that occurred in 2015. On this map, areas of known induced seismicity are shown in black boxes. There's areas of possible induced seismicity in red, though most of these boxes are now pretty well considered actual induced seismicity areas. There's several different ones over here in Colorado. All of these have really interesting stories. I'm not going to focus on them today, but feel free to ask me. They're fun stories. Right now, though, I'm going to focus on Oklahoma, because this is where a large amount of those earthquakes occurred. And it really was in the news, really from 2009 through 2016. There was multiple greater than magnitude 5 earthquakes that were really widely felt. And the largest earthquake in Oklahoma occurred in Pawnee, Oklahoma in 2016, and it was a magnitude 5.8. A lot of people felt it. So here again is earthquakes from the central United States. This is showing earthquakes from 1973 through 2015. All the blue dots are earthquakes that occurred from 1973 to 2008. Right around 2008 is when that oil price went up a lot and oil and gas production went through the roof. So the red dots are showing magnitude 3 earthquakes. Sorry, these are all magnitude 3, so felt earthquakes. And the red dots are showing them from 2009 through I'm sorry, the shot keeps changing on me. And I can't see the slides, so I can't point to things. So if you can see the slide, those red earthquakes are from 2009 through 2015. There we go. Now I can see it. And this graph is showing the number of magnitude 3 earthquakes above magnitude 3. So this is the cumulative earthquakes through time. You can see this blue line, which is 1973 through 2008. This is on our lovingly called hockey stick graph. This first time period, the slope of this line is the seismicity rate because of the amount over time. And you can see it's a pretty steady rate in the central US. It stayed the same all the way until that oil and gas really started being produced in large volumes in Oklahoma in particular. And then we have the rate of the seismicity increases dramatically. And most of this dramatic change is from Oklahoma. So I have a video that I'm going to show. This is just a screenshot. It was created from the USGS and the Seismic Sound Lab that is out of Lamont Doherty Earth Observatory at Columbia University. It's going to show earthquakes from 2004 through 2016 in Oklahoma, and it'll show it through time. I'm going to back it up so we can start it. The earthquakes are sized by magnitude, and also the sound is by magnitude. There's different colors. It didn't have a great description. I'm pretty sure it's depths, but I don't remember which are deeper. So I apologize for that, but it's pretty interesting to hear the sounds. So the really big earthquake that's kind of in the north part of Oklahoma, that is the Pawnee earthquake, which is the 5.8 earthquake that happened in 2016. Right at the end of 2016, or kind of the mid part of 2016, if you remember, oil prices dropped a lot, and so the earthquakes decreased, and that's because there was less production because of the price. So less produced water to be injected. There's thousands of wastewater disposal wells all throughout Oklahoma, and that's really the cause of these earthquakes. Okay. So I'm going to talk about what actually triggers or causes the injection-induced earthquakes. I'm going to talk about two main physical triggering mechanisms. Really widely accepted is pore pressure increase, and this is where you have fluid being injected into the subsurface that increases the pressure. That pressure then will diffuse or move farther away from that high pressure area. I like to say nature is lazy, so things always go from high to low. And so as the pressure increases near the well, it'll diffuse or propagate away from the well, and it might find a fault that is really close to failing. We call it critically stressed, and that little bit of pressure change can actually induce the earthquake. Another mechanism we'll talk about is earthquake interactions, how the earthquakes themselves can change the stress on the fault and then cause more earthquakes. So how that pressure really works is, so like I said, you have increased pressure, it propagates to one of those critically stressed faults, often in the basement, so you can have larger earthquakes. And then you have a fault that's blocked, and you have pressure or stress pushing and keeping that fault from moving. And as you have pressure increasing in the fault, it pushes back against it and allows the fault to more easily slip. If you're familiar with Moore diagrams, you have the effective normal stress decreasing because of that increased pore pressure, and it's being brought closer to the failure line. Not perfect, but I think decent analogy would be an air hockey table. So if you've ever played air hockey, before the air comes on, that puck doesn't really move very well. But then when you turn the air on, it pushes against the puck and it's more easily slipping or moving. So the other mechanism are the earthquake interactions. And this is one I've looked at a lot more in recently. And this is called Coulomb static stress transfer. But I'm going to call it earthquake interactions. It's a little easier to say. And this is, like I said, just where an earthquake itself, the slip on a fault, is transferring stress to another area. This kind of butterfly diagram is often what the modeling of this looks like. This is an example from the stress change from 3 earthquakes in the early 90s in California, the Landers earthquake, the Big Bear earthquake, and the Joshua Tree. Those are all greater than magnitude 6 earthquakes. And what I really want you to take away from this is that the warm colors, areas of red and yellow, that is areas of increased stress. So it's areas where you're more likely to have an earthquake. It's being brought closer to failure. And then the cool colors, the blues and purples, are areas of reduced stress. So you are areas that are less likely to have earthquakes brought further from failure. So I'm going to talk about a case study in Pohang, South Korea, that I've worked on recently. This is actually a geothermal energy system, but it was before the system got started. This is an example of 2 test wells that they drilled, one that's completely vertical, one that deviated slightly just because of a drilling problem. And these wells were tested to see if they could make a system here. And Pohang is really close to the coast, kind of between South Korea and Japan, and it's a decent sized city. And so they tested these wells, 5 stimulations. They were injecting at very high pressure so that they were fracking the well, but they weren't using any proppant, any of that sand, so the fractures closed once they stopped injecting. So this graph is showing through time, all those purple dots are magnitude of earthquakes, and then the other lines are showing the injection in blue, and then the flowback in this orange color. And the flowback is just the water that came back out of the well after they stopped injecting, and that was just from the pressure gradient. So it moved up by itself. So after, or right during the 3rd stimulation, they had a magnitude 3.2 earthquake. During each of the stimulations, they had small magnitude earthquakes, but this is the first felt earthquake. And then after the 5th stimulation, 2 months after it, they had a magnitude 5.5 earthquake. And this earthquake caused significant damage, over $75 million of direct damage to buildings and things. A lot of people were injured, and there was actually 1 fatality. So it was a pretty big deal for Pohang. They don't often get earthquakes. So after this occurred, South Korea put together a team to see if the earthquakes were induced. Spoiler, they were. And part of that was looking at could the different mechanisms actually induce the earthquakes. And so there was some pore pressure modeling done. This is using a computer model to measure how the injection of the fluids changes the pore pressure in the surrounding area. So all of these are cross sections, so cutting into the earth and looking from the side. Close to where the earthquakes occurred, all those yellow stars are, on the top is the magnitude 3.2, on the bottom is the magnitude 5.5. And what I want you to take from this is These are at the time of this earthquake. This color bar is showing the stress change, and anything that's lighter blue or above could trigger an earthquake. And you can see both of these stars are well within that. And then for the 5.5, so is this. So just from the injection, just from the pore pressure change, you could have had induced earthquakes. Then I wanted to look at earthquake interaction. So I know this is really small. I wanted to show you, though, kind of the butterfly diagram. What I did is I modeled, using a computer program, all the small earthquakes to see how they change the stress in the next earthquake location and at those two larger earthquake locations. And this is showing the stress change from all the earthquakes before the magnitude 5.5 event. And you can just see there's areas that are brought closer to failure, the reds and yellows, and places that are brought further from failure, the blues. So the results we got, all of these graphs show the stress change on the y-axis and the time on the x-axis. This first row is the magnitude 3.2 event. The bottom row is the magnitude 5.5 event. So these are the results at the locations of those earthquakes. This first column is showing pore pressure change. Anything on any of these graphs above 0 means it's been brought closer to failure. It's more likely to have an earthquake. So this first row with the pore pressure change, you can see at both locations, this is when the 3.2 earthquake happened. This is where the 5.5 earthquake happened. Pore pressure was above 0, like we said, so it could have triggered the earthquake. When I looked at the Coulomb stress change, earthquake interactions, there was a minor increase before the 3.2, and then when the 3.2 earthquake happened, the stress dropped at that location. That's what we expect. But at the 5.5 event, right after that magnitude 3.2 earthquake, we had a really large increase in stress. Larger, much larger than the pore pressure. So in this earthquake that happened after injection stopped, the earthquake interactions really played a role. So kind of putting it all together, what we propose as the mechanisms for inducing earthquakes is when you inject fluid into the subsurface, increase pressure, that pressure propagates away, finds a critically stressed fault, and small earthquakes start occurring. When injection stops, pore pressure actually keeps propagating away because you still have higher versus lower further away, and then more earthquakes keep occurring, you have earthquake interactions. And then further in time, you might have a large earthquake caused both by pore pressure increase and the earthquake interactions. So how this relates to mitigation is because most mitigation is done using what's called a traffic light system. This is an example from Alberta, Canada. Usually what's set up is that you have some kind of threshold that below, any earthquake below this magnitude is fine, keep going. Then you'll usually have what's a yellow light, which is earthquakes that are above this magnitude. We should start thinking about, in this case, they have to do some kind of response plan. And then there's usually a cutoff where if you have any earthquake, this magnitude or larger, shut down, and then we're going to figure it out. But that can cause some problems if you agree with me that pore pressure and earthquake interactions actually are driving earthquakes. So looking at all three of these arrows, from the beginning towards further in time, you're going to have some kind of injection start. The pore pressure starts increasing and diffusing away from the well. You might have some small earthquakes starting. They start some earthquake interactions. And then you have a large earthquake or a larger earthquake. So maybe a yellow light, they have to decrease the injection rate. You still have pore pressure diffusing. The earthquakes are still interacting and causing more earthquakes. And then you have another large event. So the well is shut down, but even after the well is shut down, you still have pore pressure diffusing away from the well, and all those earthquakes are still interacting. So there might be a time where you have some kind of mitigation limit, where after that time, any operational changes in terms of decreasing injection or stopping injection might not actually mitigate the earthquakes. And so understanding the different triggering mechanisms is really important to think about how we plan our mitigation techniques. And that's what I have for you. And I think Phil and I are willing to talk about and answer any questions.
Thank you, Dr. Carpenter and Dr. Brown. We received a lot of wonderful information, and we love the sounds of these earthquakes. So right now we're going to take a couple of minutes for you to write in your questions. And Phil, did you want to do your video now or
Sure,
after they're done writing their questions?
Now, we got a video to work here.
Okay.
How do I do the screen share? I know we went over that earlier. Oh, there it is. Okay. All right, so I'm going to do that. Here we go. Okay, so this shows P waves, and then S waves. S waves also have a back and forth type motion, and then surface waves. So structures don't do well with surface waves. That again.
I guess it might take a few minutes to upload, so maybe they could be writing their questions and refreshing their drinks while this is uploading. How about that? Does that work?
Not coming through?
It's taking a few minutes.
Okay.
So maybe we want to get some questions written in and get some beverages here. Okay. We have a few questions. While we're waiting, I have some announcements to make. Thank you so much for both of your presentations. They were excellent. Sorry that they didn't hear me before when I said thank you. Anyway, our next STEM Cafe is going to be a kind of a hybrid experience. People are going to be able to register for the live streaming, as we're doing right now, or they might register to be in person, but in an outside event. So it's sort of a hybrid, so that we can walk out and possibly look at the skies together. We will not be bringing our telescopes as we normally do because we're not supposed to be touching things, and so we need to abide by the rules. But you'll have two different ways to register, and if you go on to NIU's website and put in STEM Cafes, in the next couple of days, everything will be online. You can click on it, it'll give you instructions for whichever one you would like to register for. Hopefully you're going to join us. We're going to have Jeremy again talk about what's going to be in the sky. So let's say you're home, you'll be able to go out in your backyard and look at those kinds of things. Actually, Phil helped us last year with stargazing, right, Phil?
Yeah.
And we're also going to have Chris Stoughton from, he's a Fermilab scientist. He's going to be talking about mapping the universe and taking the mystery out of cosmic microwave radiation. And we're going to have Joel Napper, who is our NASA ambassador. He's going to be talking about NASA's return of astronauts to the moon, and it's supposed to be quite different than it was in the 60s. So those are two things. We still have some needs-based scholarships for some of our STEM camps this summer. So if anybody knows of some young people that would like to be in a STEM camp this summer, it is virtual, but it also is, they have lots of things that are sent to the house so that you actually are doing some engaging activities. So anyway, anybody can email me and I can provide some information for that. Anyway, we're also going, for those that are going to be attending the STEM Cafe outside, we also have an opportunity for you to, there will be a small fee, but you'll be able to get an NIU blanket. And also, we are going to be having STEM Fest in October. It may look different, but I have some highly creative colleagues that are going to make this extremely exciting for us. So we also go on to NIU's website and put STEM Fest in a few weeks. You'll probably have quite a bit of information about what we're going to be doing. I also just received a quick email from Jillian King Cargile, who is doing a free webinar. You can go to STEM Read for information on the NIU website. And it's going to be a partnership between STEM Read and the NIU libraries. And the series is called Present Future Telling Science plus Fiction Webinars. The first session is going to be free next Wednesday, July 22nd from 6:30 to 8:30 p.m. You can learn more about the series and the free registration at go.niu.edu/futuretelling. Anyway, there are going to be several authors, and they have some quite unique books that will be wonderful to hear them talk about future telling. Anyway, you can go on again and put in the NIU website and just put future telling in there and you get all the information. So how are we doing? Is your video ready?
Try it again here. Let's see. Okay. If it doesn't work, I have some other videos that I can show too. Go to share screen again. Okay. How's that? Anybody see that?
No, it's just spinning so far.
Yeah, I don't know if that's going to work or not.
Well, while you're working on that, we can take a few questions. How about that? Okay. It may happen. If I can move this over so I can get the questions. The first question we had was about the sandwich fault, and they wondered if it was an active fault.
Okay, I'm going to try and get back to what was that? It's not really an active fault. There's no evidence right now of movement on that fault. There was a paper published about 5 years ago that thought that the 1909 magnitude 5.1 quake might have occurred on that. That runs through southern DeKalb County, which is kind of interesting. It's a close by fault. I don't know if we can get back to my PowerPoint at all. I want to look at that map again that I showed.
I don't know. Megan, do you remember how you were supposed to do that?
Let's see. I also have it on my screen, but I don't know if that sharing the screen thing works. Try it that way. I'm going to try this again. Anybody see this?
We can see your PowerPoint now.
Good. Okay, excellent. Go down to that map. There. Can anybody see this coming through?
Yes.
Oh, good. Okay. So
PowerPoint.
yeah, I'm running it right off my screen now. So there's your P wave. Okay. There's your S wave. And then your surface wave, which dies out with depth. You put all three of them together. So you get the P wave first, then the S wave, and then the surface wave comes through. Let's go on to the map here. There we go. Let's see. I apologize that my pointer wasn't visible. I wasn't using the right pointer last time. Can you see my pointer now?
Yes.
So Sandwich Fault runs from near Joliet up to about Oregon, Illinois. And then there's another fault called the Plum River Fault Zone, which runs from about the state line over toward Byron. But again, the red dots, which show the epicenters, none of them are on any of the map faults in the area. So the solid red dark lines are the faults. There's an area over here in Chicago called the Des Plaines Disturbance. It's probably an old meteor impact structure. There's some faulting over there.
So does that mean that the Sandwich Fault is inactive?
Probably. Now this 1909 earthquake has been located in like 4 different places. And one author did place it, go back, somewhere near the Sandwich Fault. There's no evidence of breaking of the ground or any shifts or anything that are recent. Again, this whole area is covered by glacial deposits. There's only a couple of exposures, but the exposures don't indicate any kind of shifting or movement on the fault. So because of all the red dots scattered across the state here, we know there are other faults that are active. We just can't see them.
Okay, should we take the next question?
Should close this probably.
Okay, the next question we have, hopefully somebody understands it. What do you suggest in lieu of the traffic light approach?
Yeah, I'll take that one. That's a really great question, and I'm not going to have a great specific answer. A lot of this depends on the specific areas of induced seismicity. There's also some problems of not knowing where all the faults are. All of the faults that had the larger than 5 magnitude earthquakes in Oklahoma were not maps until earthquakes occurred. So it is hard to set up these types of systems ahead of time. And depending on where you are is also going to change the risk. So for example, in Canada, in Alberta, where that magnitude 4 is the cutoff, that's pretty moderate sized earthquake for the middle part of the U.S. But in Canada, where the oil and gas is being produced, there's almost no one there. So there's not the same risk as in the central United States or other places. So it's very site specific. And I don't know the answer to what's the best alternative, but there probably needs to be something besides that.
Okay, our next question is, does Oklahoma run the risk of liquefaction, is that it? Like San Francisco during the Loma Prieta earthquake, with all the earthquakes, deep well injection plus aquifers. Could massive area collapse? You could probably deal with this better than me.
So in Oklahoma, there hasn't been large liquefaction. There has been some sand blows, which are similar to liquefaction, where the pressurization causes you to have sand being blown to the surface, but it is not the same as where you have the big areas of liquefaction, like in San Francisco or Alaska or Mexico City. I don't know if there's any area, I don't know if I can say all of Oklahoma, but where the earthquakes have happened so far, there hasn't been.
And the next question is, doesn't an earthquake relieve stress at the focus and usually transfer that stress further down the fault? Therefore, a later earthquake could happen regardless if there is injection and increased pore pressure. How do you determine how much is injection pore pressure related?
Okay, I think I know what you're asking. So in the terms of the injection-induced earthquakes, they tend to be in areas that don't have the same amount of natural seismicity. And so the earthquakes, like in Oklahoma, there were a certain amount of earthquakes that occurred every year, but the amount of them was way over the norm and correlated really well in terms of time and location. What I was looking at, though, in Pohang, which might be more specifically what you're asking, is I was looking at how those small earthquakes that were definitely induced were changing the stress at a specific location where those larger events occurred. And so those earthquakes were transferring stress to that area. That's what I was looking at. And all of those were induced earthquakes. In terms of the pore pressure, when we model pore pressure, we're looking at the change in pore pressure caused by the injection. So it's not absolute values of pressure in the aquifer, just the change in pressure caused by the injection. And sorry, I'm trying to go back to the question so I can, it keeps moving on me.
I'm sorry, I might have taken it off.
Okay. I'm not sure if I caught all of that answer then.
Maybe the person can write it in again if they still have questions. All right, the next question or comment. The injection fluid is usually made up of water and silica sand, pure white sand, which can afford to be shipped long distances, usually by rail carload. That was a comment. Okay.
Yeah.
Did I?
A lot of that sand is from the Midwest, like in Wisconsin.
Right. Is there a way to model or otherwise predict the effect of the diffusion of stress resulting from an injection or other directly human-induced activity, and B, interacting earthquakes?
Sorry, I'm reading it a little more closely. So what we are modeling is the stress diffusion. So we're modeling the pore pressure change. And you can predictively model if you have the parameters of the aquifer that you're injecting into, things like properties of the rocks, and then also injection scenarios. So how much are you injecting? At what rate are you injecting? The earthquake interactions is a little trickier to predict because for a variety of reasons. The modeling of the earthquake interactions is very sensitive to the earthquake location and the what's called strike and dip and rake, so how the earthquake actually moved. So usually you're kind of going from, earthquakes that already occurred forward. There has been some like probabilistic models that are looking at the types of faults that they know about in Oklahoma and trying to put some kind of probability that it'll have induced earthquakes based on the injection around it, and then also how the fault is oriented, because there's a certain stress regime in Oklahoma that is more likely to have certain types of strike slip faulting, and so you can tell by the orientation of the fault which ones are more likely to have earthquakes.
All right, here's a question. Is there a way to model or otherwise predict the effect of the diffusion of stress resulting from an injection? Is that what you just answered?
Yes.
Okay, the fault that runs from Mississippi River to Byron. Did someone think about the Byron nuclear power plant being built on a fault?
Yes, actually, they knew the fault was there. I think actually some of the excavations near the plant uncovered parts of that fault. But they knew it was there. It's just no activity on that fault whatsoever. So there was a lot of planning done for the nuclear plants. They have to do a regional seismic analysis whenever they build a nuclear power plant. And I think for northern Illinois that they came up with an idea that maximum credible earthquake that could occur is of 6 in this area, magnitude 6. So that plant is built for at least a magnitude 6 earthquake. But there's been no activity at all on that fault. And again, if you look at the red dots, they don't seem to, none of them are really that close to where it is.
Nevertheless, it seems rather scary to me. Some of the red dots seem to follow the Rock River. Is there a relationship between any underlying fault and the course of the river?
Good question there, too. Can we switch back to my screen? I'll put the PowerPoint back up. Do that. Share screen. There we go. Okay. Everybody see this? The map?
No.
Can I get the share screen button? It was up a while ago. Can I share my screen here? I know there was a button to share my screen. It would be easier, but okay. There it is. Okay. How's that?
It's working. Trying to work.
Anyway, yes, there does seem to be some, you follow it all the way from the 1909 epicenter down to that cluster 1909, 1913, to the Quad Cities. Yeah, it looks like they kind of follow the river. There could be a geological reason for that. Often rivers follow faults, weak zones in the rock. I don't know if this is going to load or not. Also, there's an idea that pore pressures, like Megan was talking about, can be increased naturally as well by high water tables. And there's been some discussion that rivers transmit, if they're especially at high levels, pore pressures down to a fault that's just ready to slip. don't think that's going to load. We can move on, I think, then.
Okay, what is the biggest thing you want us to take away from each of your presentations?
You like to?
Megan,
You
you
want
want
me to go first?
Sure.
I'll start. Probably that it's complicated. So anytime I talk about oil and gas, I like to go into the ideas of geopolitical ramifications, economic ramifications, in addition to induced seismicity. I didn't even touch on in the environmental issues because there just wasn't enough time. But that it's complicated, and that induced earthquakes are really cool, and something that if we have high rates of oil and gas production, which seems not to be happening as much right now because of oil prices, we really need to think about how to mitigate it in an appropriate manner, because there's a lot of areas, Oklahoma, that didn't have earthquakes in that way before. And they went several years where they had more felt earthquakes than California. And the building codes aren't the same, and it was quite detrimental to people's mental health. There was actually a paper that showed that there was more car crashes after the large earthquakes in Oklahoma. And so I think those are the main things.
I guess from my presentation, I just want everybody to realize we do have earthquakes in northern Illinois, and there are faults here. And so we're actually overdue now for another felt earthquake. There's probably very little risk from these earthquakes really causing any kind of damage. But we do have an earthquake history going back about 200 years.
Well, we had an earthquake when I had my second son in Downers Grove. So I called somebody into the hospital room to ask them to please turn off the vibrator on the bed because I had had a cesarean. And she goes like, "I'm sorry, it's an earthquake." So that tells you something about my son if you come in on an earthquake, right? So thank you for those comments. Here's another question. Is there an accumulation of displaced, transferred stress or relaxation as a result of human activity? Is it possible that there will be much larger magnitude events from the accumulation of non-natural inputs?
So I would say the size of the earthquakes definitely are controlled by the fault size. So there are certain areas where the induced earthquakes, you can't have a larger earthquake because they're happening on smaller faults. But there's definitely areas where that's not true. We've had magnitude 5.8 earthquakes. What usually we describe as it's not so much that the human activity is making the earthquake happen. They're triggering them from those critically stressed faults. So instead of kind of making larger earthquakes, we're just speeding up when the earthquakes would occur. I'm not sure if that fully answered your question. Hopefully it did. Write in if it didn't.
Phil, did you have any comment about it?
Do you want to add anything, Phil?
Let me take a look here again. What up?
I can repeat it. If there's an accumulation of displaced, transferred stress or relaxation as a result of human activity, is it possible that there will be much larger magnitude events from the accumulation of non-natural inputs?
I think, Megan kind of stressed that it depends on the size of the fault, the amount of stress that's existing there. Probably in terms of magnitude, probably not larger magnitude events, but more events, definitely. So like that area in Oklahoma that had the magnitude 5 earthquakes, they'd never had any that big before in that area. Not sure. I know there's a couple of faults there, but there's definitely been an increase in activity.
Well, I don't see any other questions. So I do want to thank both of you for your presentations this evening. And I want to conclude by, again, sharing some of our upcoming events. I want to thank also Aline Plick, Director of Web Media and E-Learning, and her staff, Raz Adul Sarani, for helping us out this evening. And you will find this recorded STEM Cafe in about a week, as we have to worry about the closed captions, and it takes about a week to get it up there. But all of our virtual STEM cafes that we have had, this is our 7th one, are online. If you go to NIU website and just put STEM Cafe in there, you will find the upcoming STEM cafes. You'll find the recorded ones. And so it's all there in case somebody missed something or wants to go back for it. And you never did get the video working, evidently, Phil?
Actually, well, I didn't get that one working, no. I did have that earthquake video. I don't know if anybody would like to see some of that. It shows that large earthquake in Japan. I can try to put that up and see if it works. Let's see.
Well, he's trying to get that to work. I also want to remind you of our STEM Fest will be in October, and we will have more details on that in the next couple of weeks. So it's definitely October, so please stay tuned and pay attention to that. And it sounds like you have it.
Is it working?
Yes.
You guys see this? Here's some pictures from a 2011 quake.
This is the tsunami that damaged the Fukushima nuclear reactor plant. That's it blowing up right there.
I'm going to skip ahead a little bit here. Everybody see this okay?
Yes.
Okay. Actually, this is kind of an interesting part right here. I'll select the section. So I'm going to go up here. think these are like surveillance videos.
Oh my God. Glad it was there instead of here.
There's a section near the end here. Well, this is quite interesting, the swimming pool. And then we talked about liquefaction. There's really a kind of interesting this part. Another thing that earthquakes cause are landslides. See if I can find the liquefaction part here, and we'll finish up with that. This, it's a good example of liquefaction when you see the sand coming up out of the ground like that.
Well, I'm glad we were able to show that video in the end. And again, thank you very much for your presentation. Thank you, everybody, for joining us. We hope that you will join us for our next STEM Cafe. It's always wonderful if you email me to give us some feedback on anything you would like changed or some new ideas for STEM Cafes. We always welcome any of your input. And if you know anybody that would like to sponsor a STEM Cafe, I would be very grateful. So please share that information with anybody that you know of that is a potential person that would be willing to sponsor a STEM Cafe. And again, this is recorded and it will be available in about a week. And STEMFest is in October, and our next STEM Cafe, I don't think I told you the date, is August 11th, because that is a peak meteor shower time. And it will be located at the Bliss Creek Golf Course, but it's at the Open Range Southwest Grill, 1 Gulfview Lane in Sugar Grove. You may come at 6 o'clock if you're looking for. We have some picnic tables that will be outside, but we encourage you to bring your umbrella chairs and a blanket or whatever because it's going to be outside. If it should rain, we're going to scoot everything on the inside because actually the Pine Room is a pavilion, so we still will be okay. We can only limit it to 50, so when in a couple of days you might want to go on to NIU's website and put in Stamp Cafe. There'll be two types of registration. Registration like this for live streaming and registration for the outdoor event. And again, it's limited to 50 people and maximum groups of 4. Anyway, please go online and get more information. And we hope to see you there. It's our annual stargazing event, and we always have a fun time. And thank you very much. Yes.
Can I answer Kathy's question really quickly? Where to go during an earthquake? You want to get under a piece of sturdy furniture. The going in a doorway is a myth. Don't do that. And it's, depending on where you are, you probably don't want to go outside either, especially in cities because glass can be falling. So under and it's hard to walk. So under a sturdy piece of furniture.
Were there any other questions I missed? I never saw that one.
Is there a way to minimize the impact and environmental damage due to fracking? That's another STEM cafe. The answer is yes, but it's another STEM cafe.
Oh, I see. There are some more down here. Okay, so I think we got it all. Thank you very much for being here this evening. We really appreciate it. Have a good evening.